Alright Sudhir, let's dive straight into the dimensionless number from our interface flux chapter. These numbers are basically tools, smart shortcuts to compare and predict the behavior in different systems, right?
Exactly, Ved. Instead of dealing with the raw units and variables, we use these dimensionless numbers to characterize flow, heat transfer, mass transfer, and more. They help in generalizing results so we can apply them across different systems without redoing all the math.
Reynolds number, which is also denoted as RE. Let's begin with the king Reynolds number. It is defined as RE equals to rho V L by mu, where rho is density, V is velocity, L is length, and mu is dynamic viscosity.
Right. Physically, it compares inertial forces to viscous forces. So when RE is high, inertial effects dominate, meaning the flow is turbulent. When it's low, viscous forces dominate, so the flow is laminar.
And in interface momentum transfer, it helps determine how the momentum is diffused across the surface, whether through smooth flow or chaotic eddies.
So now we have Nusselt number Nu. Nusselt number Nu can be defined as Nu equals to HL by K. That's convective heat transfer coefficient into length over thermal conductivity.
It tells us how effective convective is compared to pure conduction. If Nusselt number Nu equals to 1, there's no enhancement from convection, just conduction. Higher Nu, better the heat transfer.
Exactly. It's a key outcome when analyzing heat transfer across interface and relates directly to the temperature profile around the surface.
Sherwood number SH. Now the mass transfer counterpart of Nusselt, the Sherwood number. SH Sherwood number equals to KCl by D, where Kc is mass transfer coefficient and D is diffusivity and L is length.
Just like the Nu compares convection to conduction, Sherwood compares convective mass transfer to molecular diffusion. So if you're analyzing a dissolving gas bubble or a solute diffusing in a liquid, SH gives you the intensity of that mass transfer.
Prandtl number PR. This one connects viscosity and thermal conductivity. PR equals to mu Cp by K, which is also equals to nu by alpha, where nu is kinematic viscosity and alpha is diffusivity.
It is essentially compares how fast momentum diffuses versus heat. For example, in air, PR is equals to 0.7 approximately, which means heat diffuses faster than momentum. In oil also, PR is much higher, so momentum diffuses faster.
And it helps in heat transfer correlations, especially when combined with Reynolds number and Nusselt number.
Now we have the Schmidt number SC. Now replace thermal conductivity with mass diffusivity, and you get the Schmidt number SC equals to nu by D.
So again, it compares momentum diffusivity to mass diffusivity. If SC is high, momentum spread faster than mass. Think about gases, where diffusion is quite rapid, SC is low, but in viscous liquid, it's high.
Exactly. Now we have the Lewis number Le. This one bridges the thermal and the mass transfer, where Le equals to alpha by the diffusivity, D equals to K by rho Cp into D. It tells you how well the heat diffuses compared to mass.
So for air, Lewis number is approximately equals to 1, which means heat and mass diffusion at similar rate. But for liquid, especially mixtures, Reynolds number, Lewis number Le can be vary a lot, affecting how concentration and temperature profile develops. Start.
Now we'll understand dimensionless numbers from the interface flux and the molecular flux that is given in the slide that is shown there.
Alright, Sudhir. Let's break down these slides on dimensionless number. Let's start with comparing interface flux to molecular flux and how we can use this ratio to understand transfer efficiency in simplified and unitless way.
Yes, the slide gives us three equations labeled A, B, and C and then combines them. Let's take each one slowly.
So now we will discuss equation interface flux. So equation A says interface flux equals to transfer coefficient multiplied by difference in the quantity per volume. Let's understand what that means. Interface flux is the amount of something like heat, mass, or momentum that's being transferred across an interface, say between a solid and a fluid. The transfer coefficient is just a measure of how easily the transfer happens at that interface. The difference in quantity per volume is the driving force. For example, a temperature difference or a concentration difference. So this equation says greater the difference and the more efficient the surface is, the higher the flux is.
Then we will have equation B, that is the molecular flux equation. Right now we have equation B, that is the molecular flux equals to diffusivity into gradient of quantity per unit volume. This one is about what happens naturally and in the fluid or medium itself without any interface. Think of it as a built-in spreading due to molecular motion, like how dye spreads in water. Diffusivity tells us how easily molecules move or spread. Gradient of quantity per volume means how sharply something like concentration changes over time. If the gradient is steep and diffusivity is high, molecules spread faster, increasing the molecular flux.
Let's discuss now equation C. Equation C connects the gradient to something we can measure more easily. Gradient of quantity per volume equals difference in quantity per volume divided by characteristic length. So instead of directly using a gradient, we approximate it using the difference across a small distance. This is what we call the characteristic length. That could be thickness of a layer, diameter of a pipe, or whatever length scale is relevant. So now we can rewrite the gradient in equation B using this.
Now we'll combine equation A, B and C. This is where the main point of the slides comes into picture. We have equation A, interface flux, and divided by equation B, molecular flux, and we have to substitute the gradient using the equation C. This gives us interface flux divided by the molecular flux equals to transfer coefficient into characteristic length divided by diffusivity. This ratio is dimensionless, meaning it has no units. Everything cancels out, length, time, etc. That's why we call it the dimensionless number. Now, tell me about the interpretation of this thing.
So what does this dimensionless number tell us? It compares how much is being transferred at the interface versus how much could be the transferred naturally by molecular diffusion. If this ratio is high, it means the interfacial process is very effective. It's transferring a lot more than diffusion alone could. If the ratio is close to 1, then the interface transfer is about the same as diffusion, meaning there is nothing extra helping the process.
Now to summarize the slide we have, it builds a basic definition, interface flux, molecular flux and gradient. Then it relates them together to form a dimensionless ratio. This ratio gives a simple way to compare with different systems or conditions without worrying about the units.
Exactly. And this forms the base for many other engineering tools. But even without going further, this basic comparison helps us to understand how strong or weak a transfer process is in a given system.
3, 2, 1, start.
Let us now discuss the slide that introduces the concept of generalized transfer coefficients and the associated dimensionless numbers, especially focusing on the expressions leading up to the standard number.
Yes, this slide is important because it attempts to unify the mathematical representation of different transport processes like momentum, heat and mass through a consistent framework. This is achieved by expressing their respective transfer coefficient in terms of characteristic velocity denoted by VCH.
The slide begins by representing three different expressions, each representing a form of transfer coefficient. First, half F VCH. Second, H upon rho Cp. Third, Kc. Let us go through this one by one. First expression, half F VCH, arises from the momentum transfer context. Here, F is the frictional factor and VCH is the characteristic velocity of the flow. This expression essentially reflects how momentum is transferred between fluid layers due to the viscous effects. The second expression, H upon rho Cp, corresponds to heat transfer. In this case, H is the heat transfer coefficient, rho is the density of fluid, and Cp is the average specific heat at the constant pressure. This ratio is used to express the heat transfer coefficient in terms of an equivalent velocity scale, ensuring compatibility with momentum transfer analogy. The third expression, Kc, is the mass transfer coefficient, which directly represents the ability of a system to transfer mass across an interface.
The key idea presented here is that all three transfer processes, momentum, heat, and mass, can be characterized in terms of velocity. The slide uses an arrow to indicate that each of the above expression can be equated to a common form of velocity, especially the characteristic velocity VCH. This allows for a generalized interpretation where each transfer coefficient is expressed by the velocity unit. This approach is useful because it provides a unified framework for analyzing and comparing different transport processes using a common baseline velocity. It also simplifies mathematical modeling and makes it easier to establish analogies between different modes of transport.
Now we will define standard number. Moving forward, the slide introduced two important dimensionless numbers, both categorized as standard number. First, the heat transfer standard number, which is given as denoted as STH, equals to H upon rho Cp into VCH. Second, the mass transfer standard number, which is denoted as STM, equals to Kc upon VCH. Let us interpret this in more detail. For heat transfer, the standard number STH is a ratio that compares the rate of convective heat transfer to rate at which the heat is carried out by the fluid. Especially the numerator H represents the convective heat transfer coefficient, while the denominator rho Cp into VCH represents the heat carrying capacity of the fluid due to the bulk motion. The higher the standard number, the more efficient the heat is being transferred relative to the fluid movement. Similarly, the mass transfer standard number STM compares the rate of mass transfer, represented by Kc to characteristic velocity VCH, indicates the effectiveness of mass transfer in relation to the fluid motion.
Let us now define the physical interpretation and the importance. These standard numbers are very useful because they allow us to assess the efficiency of a system. In practical terms, they help engineers and scientists understand how well a system transfers energy or mass related to the fluid's capacity to carry those quantities. A low standard number may suggest that transfer is slow compared to the fluid motion, indicating the need for design improvements, such as increasing surface area, introducing turbulence, or modifying material properties to enhance transfer. On the other hand, a high standard number indicates that the transfer process is fast and efficient related to the fluid motion, which may suggest that the system is already performing well or even over-designed in certain contexts. Where now you tell the conclusion.
To summarize, this slide represents a contrast between powerful way to bring together momentum, heat, mass transfer using single characteristics velocity. By expressing transfer coefficients as an equivalent velocities, it becomes possible to define dimensionless number, such as the standard number, which provides meaningful insights into the effectiveness of transport phenomena across the different systems.
Indeed, the ability to compare these different transport processes of the same scale is extremely valuable in both theoretical understanding and practical engineering design. The generalized framework introduced here lays the foundation for such analysis.
Discuss three equations. First, John Thomas Fanning equation, which is equals tau w equals half rho v infinite square into f, which we can also write as half rho vch into f into delta vch. Now, second equation which we will discuss is Newton equation, which we can write as qw equals to h into tw minus t infinity, which we can also write as qw equals to h into delta t. Now we will discuss our third equation, which is Slater equation, which we can write as NAW equals to Kc multiplied by CAW minus CA infinity. which we can also write as Ca into delta Ca, Kc into delta Ca. Now, now writing the interface flux formula, which equals transfer coefficient multiplied by difference in quantity divided by volume. We have discussed three equations before, and to match their dimension with this interface flux formula, we can modify them as first equation can be written as tau W equals to half F into VCH into delta rho VCH. Second equation can be modified as QW equals to H upon rho Cp multiplied by rho Cpt. And third equation can be modified as NAW equals to Kc into delta Ca. The dimensions are same, so no need to change this equation. Now we will mark this equation as 1, 2 and 3. And we can also notice that the dimensions are same for half rho VCH, H upon rho Cp and Kc. Now we will write it separately. These are transfer coefficient. And for half F into VCH, we can directly write it as VCH as our half and F are dimensionless. Now we will derive heat transfer Stanton number, which is also denoted as STH, which equals H upon rho Cp multiplied by VCH. Now we will derive Stanton number for mass transfer, which is also denoted as STM, which equals Kc by VCH. Now again writing the three equations, interface flux equals to transfer coefficient multiplied by difference in quantity by volume, and marking it as equation A. Now writing molecular flux form equation, which equals molecular flux equals to diffusivity multiplied by gradient of quantity divided by volume, and marking it as equation B. And our equation C is gradient of quantity divided by volume equals difference in quantity divided by volume divided by divided by characteristic length. Now combining these three equations A, B and C, we will get a new equation which is interface flux upon molecular flux equals transfer coefficient multiplied by characteristic length whole divided by diffusivity. Now we will make a chart where we can write process. Our second headline, first headline is process. Our second headline is transfer coefficient. Our third headline is diffusivity. And our fourth headline is interflux phase flux upon molecular flux. So first process is momentum transfer process. Transfer coefficient in momentum transfer can be written as half F into VCH. Diffusivity can be written as mu upon rho, and interface flux divided by molecular flux can be written as half F rho VCH into LCH divided by mu. We can also write this interface flux upon molecular flux as half F into RE. RE is nothing but rho VCH into LCH divided by mu. Now our second process, which is energy transfer. Transfer coefficient can be written as H upon rho Cp. Diffusivity can be written as K upon rho Cp. And interface flux upon molecular flux can be written as HLCH by K, which equals Nusselt number. Now our third equation and last equation, which is mass transfer process. The transfer coefficient is Kc, diffusivity is DAB, and interface flux upon molecular flux can be written as Kch into LCH divided by DAB, and which is also equals to Nusselt number for mass transfer, NUM, which is denoted as NUM, which also equals Sherwood number.
Now we'll try to solve some simple questions on this Reynolds number, Nusselt number, and Sherwood number. The question one as follows. The question one says a fluid is flowing over a flat plate, sorry, over a flat plate with the following properties.
properties. So the friction factor is given as 0.04. Characteristic length is given as 1.2 meter. Characteristic velocity is given as 2 meter per second. Density, fluid density is given as 1000 kg per meter cube. Dynamic viscosity mu is given as 0.001 Pascal per second. Check the units for the question. So let's start the question. We need to find half F into RE and interpret its meaning. What does that actually mean? So the solution as follows. We have RE as rho VCH LCH upon mu. That is equals to 1000 into 2 into 1.2 divided by 0.001. That is equals to 2.4 in 10 to the power 6. So half FRE can be given as half into 0.04 into 2.4 into 10 to the power 6. That is 48. Sorry, that is 48,000. Right? So what does that actually mean? This means, let's change the color for. This means the transferred, momentum transferred is 48,000 times faster via convection than by viscosity alone. Via convection than by viscosity alone. Now let's to the next question. The next question says a hot gas flows past a surface, right? So the following parameters: heat transfer coefficient H is given as 60 watt per meter square Kelvin. Characteristic length LCH is given as 0.25 meter, and thermal conductivity K is given as 0.03 watt per meter Kelvin. Very simple question. We need to find the Nusselt number. Nusselt number is generally calculated for this energy transfer systems, right? So let's calculate the Nusselt number. What is the formula of Nusselt number? Nusselt number formula is H LCH by K. That is equals to 60 into 0.25 divided by 0.03. That is equals to 500. Right? What does that mean? This means heat is transferred. Heat is transferred. The interpretation of this Nusselt number 500 times transferred, 500 times faster via convection than conduction, right? Next we have the Sherwood number calculation. The question as follows: a a gas mixture is diffusing near a solid surface near a solid surface following parameters given: mass transfer coefficient Kc as 0.001 meter per second, LCH as 0.05 meter, and DAB as, that is diffusivity of species in A from A in B. Diffusivity of species A to B, right? So now, continuing the problem, we have the Sherwood number SH as Kc into LCH divided by DAB, nothing but 0.001 into 0.05 divided by 2 into 10 to the power minus 9. Very similar, we get is as 25,000. What does that actually mean? This means mass is transferred 25,000 times more efficiently 25,000 times more efficiently via convection than by diffusion. So we have calculated the Reynolds number, the Nusselt number, and the Sherwood number, and we have understood all the interpretation of these numbers, right? Thank you for watching this video. I hope you liked it. The video is created by Ved Patle and Shruti Chatterjee for TP assignment 4. I hope you enjoyed the video. Thank you.